Thank you, Susan. We appreciate your taking time to visit with us this morning. And certainly I know there are members of the audience who will be commenting, I'm sure. And so we look forward to what the final rule may look like and how it will be implemented as we go forward. So thank you very much for joining. Appreciate it. With that, I failed to mention this morning we had a last-minute change to our schedule. Janet Galisi is not going to be able to join us, so we are going to have a little bit of elasticity in our program this morning. So that'll give our next couple of presenters a little additional time to go through their slide decks and their presentations, as well as to allow for a little greater time for some question and answer. So if you'll bear with us, we'll try to manage our time accordingly. With that, we are still on schedule, and our next speaker this morning is Dr. Bruce Keiser, a research fellow in air protection technologies and nanotechnologies at Nalco. And he is going to talk with us this morning about reliable MATS, Mercury compliance strategies for electric generating units with wet flue gas, and I always forget what the D stands for, so I'll embarrass myself. Thank you.
Not a problem.
So with that, the floor is yours.
Thank you very much. Well, I'm not sure what I can do with more time. I'll probably go too long anyway. I'll try and keep it to the half an hour. I appreciate you taking the time to be here this morning. And I'm a little bit in awe being kind of in between regulatory information that you really needed to know and the fact that we're seeing power generation evolve in Michigan. And evolution is really the part of this presentation that I want to kind of emphasize as we go through the presentation. I promised you at least 4 things that you're going to learn from this presentation. You're going to learn about characterization, control and compliance, a strategy that puts you in control of your mercury emissions, and how to monitor and automate that process. Of course, you're looking at the left or the right side of this slide, and obviously you can look at the graph. On the left-hand side of that graph is where we are today. On the right-hand side of that graph is where we have to be starting next year. And we have to be there reliably, 24/7. I'm going to present basically the path to a reliable strategy, how to characterize and measure mercury and flue gas, and then talk about the components in building your strategy, and finally a case study. I want to start out with a question and a show of hands, because I know that I can get into a very technical meeting and everybody will go to sleep on me. So what I'd like to do is, this is interactive. How many of you fly? Okay, how many of you are actually pilots? Okay, so the pilots go to sleep right now, because I'll probably not be technically correct on what I'm going to show you next. When we started to learn to fly, we had an airplane something like this. And quite frankly, it had, hopefully it'll show up. Uh-oh. Did I push the wrong button? Okay, I give up. It's supposed to go forward. Oh, there we go. Thank you. And when they started to fly, they had an instrument panel that kind of looked like this. Very simple, kind of told you where you were going, what your engine was kind of doing, okay, and a little clock on the side so you could calculate very quickly how long you could stay in flight. Now that was great if you were flying visually, but as you know today, we fly through all kinds of weather most of the time. All kinds of weather, in the dark, okay? And so, as a consequence, aviation has gotten more complicated. And as you can see, the new cockpit, or the nearly new cockpit, has many more instruments to go by. This is the evolution of flight. Equally, there is an evolution in the power plant. An evolution in the control room from simply looking at air and fuel and mixing those and looking at your heat output and the megawatts you generated, to also looking at what else we generate. How do we control mercury as an example of a pollutant going forward? So there are basically these five steps. You have to measure it first. You have to manage the speciation of mercury in the flue gas. You have to master it within the WFGD if you're using WFGD as your strategy and your control point. You have to monitor it continuously, just like you have to monitor the conditions, the quality, the running of the engine of an airplane. And then you have to apply everything that you've learned. Okay. I'm going to let you help me in the back. There we go. Okay. This is the issue with measurement. The first and most important is making the mercury measurement in the flue gas. On the left-hand side, you will see an example of commercial measurements being done, and you can see that they are far from being accurate with regard to flue gas mercury. If you try and drive your solution based on this information, you will be going in a wrong direction. So it is important first and foremost to have total measurements that are correct. If you get the total measurements correct, then chances are you can rely on your speciation measurements as well. If you question the inlet data, then you have to question all of your data, and you begin to wonder, what is it that my unit is actually generating? Okay. Again, this is another example. This is on the left-hand side a little bit better match between carbon traps and SIMS. And as you know, there are not the measurement of mercury in flue gas is not simple. There are a few people, a few organizations that are well embedded in this technology and consistently do a good job. And as you can see, this is good, but this is obviously much better in terms of your relationship and your correlation between carbon traps and SIMS. If you're going to drive your unit based on SIMS, you better well have a good correlation with what you're reporting to the regulatory body. So insist on quality. And to keep with the analogy, the measurement of mercury is a lot like knowing what your heading is. So as a pilot looks to see what his heading is going to be based on this instrument, your measurement is the same thing. If you have a poor heading, obviously you're not going to end up in the right place. Okay. So next, let's talk about managing mercury speciation. Busy slide. You've seen a lot of this information before. You can take the time to read it while I'm speaking. But key among this is there's a lot of different forms of mercury, but if you're using a wet FGD to control your mercury emissions, you must maximize oxidation in the flue gas. That is done in bituminous coals. It's clearly correlated with chloride content, and yes, there is a certain amount of bromide content in that coal as well. Both of those halogens will increase your speciation across across the various air quality control devices. Okay, I'm going to give up here. Next slide, please. So, to manage your speciation, there are 3 different ways you can do it. You can do it based on fuel, you can do it based on fixed assets, and you can do it based on additives. Fuel is simple. You take a low chloride content, a high chloride content coal, and you mix those. Fixed SCRs will, in fact, give you the co-benefit of increasing your mercury speciation. And then additives, boiler additives such as Mercontrol 7895 provides additional halogen. It allows you to fine-tune your oxidation of mercury across the unit. In fact, the additive use will, in fact, increase or provide you with, in the absence of an SCR, somewhere between 80 and 90% oxidation, and up to 98% oxidation with an SCR present. You can see on the right-hand side of the slide, I apologize, a graph that was put together that shows the impact of age on an SCR and the fact that you will, as the SCR catalyst age, lose oxidation effect on your mercury. This is your altimeter. This tells you how high you are flying. Okay, again, it's most important for you to get the maximize your oxidation, because with wet FGDs, only oxidized mercury is removed. Next slide. Thank you. Here's a quick summary slide. It gives you some quick comparison of performance. And there's a lot of information on here. I'm going to draw your attention to the two middle examples, and we can just look at the bituminous. Let's look at comparing with and without an SCR. You can see the difference in the flue gas mercury between the two, representing a 70% oxidation and a 90% oxidation of mercury. You can see elemental with an SCR is 0.83. That is within compliance of regulations, and as a consequence, you can see as it comes through the wet FGD, assuming you have 90% capture of oxidized mercury, in the one case with the bituminous with an SCR, you are well within compliance. Okay? In the case of the lower oxidation, you can see that you are not near the limitations of the limitation regulation, and that is exactly the point that I'm trying to get across here. Next slide, please. So, if once you've prepared your unit, you've characterized your unit, you know what your mercury oxidation state is, the next step is to master your mercury across a wet FGD. Next slide, please. And again, this is complicated. Only from a visual, I'm going to simplify this for you. This is taken from a couple different places. People have been talking about re-emission being complicated, and quite frankly, it's really simple. You can make this really simple and draw a red box or a black box, however you'd like to do it, around the wet FGD operation, and basically you have, not as some people would say, two outlets and one inlet. You have, in fact, 2 inlets and 3 outlets for mercury around your wet FGD. And you can see what they are. You have flue gas coming in, which is your constant form of mercury coming in. Once it's inside the wet FGD, it either leaves through the flue gas, the clean flue gas, which is where we don't want it, or we want to control it with regard to compliance. And then it also leaves with the blowdown from the wet scrubber. Now that blowdown contains, as shown here, as Gary Blythe did it pictorially, the blue being the water phase and the gray being the solid phase from the blowdown. So it will actually leave in both of those components. And then you have another group or another source of mercury entering your wet FGD, which is your reclaim water. Any of the water that you're bringing back from the filtration of the byproduct, any water that you're bringing back from waste ponds and things like that will contain mercury, and some of those can contain very high amounts of soluble mercury. So if you're trying to manage your mercury across the wet FGD, you have to manage these, basically these 4 contributors or outlets. And within the scrubber, yes, there is re-emission, and yes, there is a partitioning of soluble mercury between the solids and the liquid phase. All of this going on simultaneously and as a result of changes that you are making in the operations up front of the wet FGD and on the backside of your wet FGD. Upfront changes being things like load. Okay? The backside being things like how fast and how much water are you putting through your wastewater treatment plant at a particular time. You have to manage all of these things. And you note that the solubility of oxidized mercury is 4.8 grams per liter. It is the soluble species coming out of flue gas. That's why you can get the co-benefit from a wet FGD. Elemental mercury being very, very insoluble. In fact, by definition, it is non-soluble. As a consequence, if it is generated within the scrubber, it actually is released back to the flue gas. And that is the reason, if you go to the next slide, please, you will actually see, and this is an illustration, a cartoon, as you will, of what you might see at your sims. You will actually see, okay, there we are, an increase from the inlet to the outlet of elemental mercury, okay, in the flue gas. If you make that measurement and you see that increase, most likely you have re-emission. Next slide. So, how does this impact your performance? There's a little bit of a cartoon here that I've taken from Sargent and Lundy. They put this together. You can see the total percent mercury removal on the left-hand side, and on the bottom you can see how much of the oxidized mercury is actually being re-emitted. The more that you re-emit mercury, the lower the efficiency is for your wet FGD, the higher your stack emissions will be. Okay? So if your mercury re-emission increases, you're going to see higher stack emissions. Next slide. Or there you go. So this is in fact your tachometer and your exhaust temperature when you're looking at a wet FGD. This is how fast you can run, and this tells you how well your FGD is actually operating. Next slide, please. It is about a holistic approach. We have been teaching this from the first presentation that we made. It is about controlling speciation coming in. It is about controlling what's going on within and around your wet scrubber by controlling what's going on inside your scrubber, inside the red box, with regard to mercury, and about controlling what's going on in your wastewater side, which controls the mercury content of that water that's being returned to your scrubber. And we want you to reclaim water. That is a good, environmentally sound practice. Next slide, please. So let's consider the final step, which is controlling mercury re-emissions, which is consistent operation, the use of additives, and then automation. So let's get into the details within the red box, okay, for a few minutes. Next slide. You have to maintain some consistency within your scrubber. The days of flying an older plane and just visual mode for your wet scrubber are gone. You have to monitor your wet scrubber consistently. Make sure that it's running consistently. Things like sulfite concentrations, chloride or bromide or halogen concentrations within your scrubber. And certainly pH and ORP are key indicators that will tell you how your scrubber is operating. These are some guidelines. I hate to put these up here, but everybody wants to see them. These are simple guidelines. They are not true for every scrubber. They may not be true for your scrubber. Your scrubber operation will have a sweet spot based on the fuel that it's running and based on the load swings and the load that it is running and the capacity. These are also not these are not methods to rapidly respond to excursions in mercury emissions at your stack. These are long-term, consistent operational variables. You cannot bring a scrubber into control by trying to increase your halogen content from 10,000 parts per million to 20,000 parts per million overnight. Okay? You will get a benefit from that, but it is not on the order in most cases that will control your excursion very quickly. Next slide, please, as an example. Scrubber additives are a group of chemistries that are added to the scrubber that will control the solubility of the soluble mercury within your scrubber. Here is a group of them. Obviously, I've highlighted, since I represent Nalco, our products, the Merck Control 8034 and 8034 Plus. These are the things that you can use that immediately change the excursion or the severity of that excursion at your stack, and can be used to control consistently and reliably the emissions based on a wet FGD. So this is, next slide please. So this is basically your oil pressure indicator. If you have this type of oil, your engine is going to run well, it's going to run smoothly, and your scrubber will pull out ionic mercury. Next slide, please. So monitoring and control. It's all well and good to simply get it started, have a wet FGD running. What is control versus compliance? So let's go to the next slide, please. Like everything else, as we were saying, evolution is coming to the running of a coal-fired power plant. You started with a few instruments. We're going to have to add more, because now we know that we have to monitor and respond to changes that are occurring within that wet FGD. We do that by continually providing a monitoring and sensor array that continuously looks at the conditions of what's going on within that scrubber. We input, in addition to that, process inputs, things that you control at the front end, things like the load, because we're going to be doing a heck of a lot more load swinging these days than we did in the past. Those all impact what's going on within your wet scrubber. Next slide, please. The benefit here is that you take a proactive response instead of a reactive response. What do I mean by that? Instead of reacting to an excursion that occurs in your stack, running around trying to figure out what you're going to do to bring that excursion down so that you can meet your limitations, compliance, okay, you do it ahead of time. We can recognize where that spike is coming from and make appropriate changes to the chemistry within the scrubber before it happens. This is your attitude indicator. This tells you whether you are climbing or diving, banking left or right in an airplane. And believe me, having some experience with this indicator, if you stay on a diving mode too long, it's not really good for you. It usually ends up with something called a crash. Thank goodness it was in a simulation. Next slide, please. So finally, let's talk about the application. Let's actually look at a commercial example on and see how it worked out. Next slide, please. This particular example is taken from a bituminous, from a unit that is burning bituminous coal. You can see the specific conditions of it described. And we were specifically looking at 2 mercury monitoring points. I'm not going to go into a lot of detail. Please trust me from the standpoint that we made multiple measurements by both 30B and as well as SIMS measurements to make sure that the 2 were reliable and the numbers we were getting were correct. You'll notice that this has an SCR. It does have a fabric filter, and then it goes through a wet FGD and ultimately through a wet ESP before it goes to the stack. The goal of this particular test was to automate mercury re-emission control. In other words, to control mercury re-emission automatically to enable compliance, to minimize unit emissions. Next slide, please. This is data collected over 50 days worth of demonstration. In this particular case, you can see the unit, which is shown here in red, which is the stack mercury. I just wanted to make sure. I was pretty sure that was right. The stack mercury is shown here in red, and you can see over these 50 days a lot of variation. In fact, a lot of spikes and excursions occurring. The green dots are soluble mercury within the scrubber. Nalco has been providing this service on site since we started. It is a critical measurement so that you know where your wet FGD is, the chemistry, and what is taking place within the scrubber almost instantaneously, or at least within 2 to 3 hours of the sample. And as you can see, in every case where there is an excursion in stack emissions, there is an excursion in soluble mercury. You also notice, and I want to emphasize this on the left-hand side, the concentration for the soluble mercury is a logarithmic axis, which means that you're seeing huge swings, 100-fold swings in the soluble mercury. Next slide. Well, before we go to the next slide, I'm sorry, I kind of jumped the gun. You can see also within this the disadvantage, if you will, of trying to treat the spike or the excursion once it's started. This is a reactive method of control, and as a consequence, you will be trying to minimize that excursion, but it depends on how quickly you catch it as to how effective you're going to be. What happens if you become proactive? Next slide, please. If you become proactive, you get exactly what I promised you from the title of the presentation. A proactive method of automation and control that gives you reliable control over your stack emissions through a wet FGD. You are now managing the mercury within your wet FGD. Next slide, please. So in conclusion, I'd like to point out that increases in stack mercury emissions are the result of mercury re-emission. Okay, it's a result of not controlling your mercury within the wet FGD. You can get reliable control through the application and then compliance through the application of control mechanisms for mercury re-emission. And then you can automate this process so that it's consistent and reliable and takes a lot of pressure and risk out of this process. Next slide, please. I want to point out here, going forward, beginning next year, you want to pay attention to the instruments. In 2013, we all read about the Dream Lifter flight that took off from New York and landed at the wrong airport. Why did they do that? Because they weren't paying attention to their instruments. This is an oops that we do not want to experience after 2015 with the coal-fired power plants. Next slide. So it is getting more complicated. I apologize for that, but it is an evolution of generating consistent electricity using coal-fired power plants and providing reliable mercury MATS compliance. Any questions?
Any questions?
One here in the front.
Great presentation, Bruce. Thanks. I had two questions, actually.
Sure.
You showed some measurements of soluble mercury in a slide. I wondered if those correlate with ORP measurement at all. And then, secondly, when it comes to testing for re-emission, obviously measuring speciation is key. In my personal experience with the use of carbon traps for speciation was that they were quite unreliable. But I understand they've come a long way since. Do you lean more towards SIMs or traps for speciated measurements? If you had to pick one over the other, which one would you pick?
Okay. Those are great questions, Rich. Thank you. The first question is whether or not there's a relationship or correlation between soluble mercury in your wet FGD liquor and the ORP. There is a correlation to some extent. It's a complicated answer, and I apologize. I'm a technologist. The simple answer is if you have an untreated scrubber there is a correlation. Gary Blythe has demonstrated this at several different locations, that there is a partitioning between the mercury, between the solids and the soluble phase. Okay, you'll go back to recall there was the blue phase and the gray phase. If your ORP is fluctuating over 200 to 300 millivolts, you're actually changing that solubility distribution with equilibrium within your scrubber. The higher the solubility concentration is, the more likely you are going to get reemission. We control reemission by removing soluble mercury because that is what will be reduced. Okay. When you go to use an additive, the correlation between ORP and soluble mercury obviously does not exist, because what we've done is we've eliminated soluble mercury from your scrubber. The second question had to do with speciation and speciation measurement, carbon traps versus SIMS. How reliable do I find carbon traps with regard to speciation? And then which would I prefer? Both systems, quite frankly, have come a long way since we first started. I was recently reading a paper that would suggest that a high level of caution be applied to numbers that were measured by either method predating 2009, simply because a lot of measurements were made not taking into account things like LOI in the fly ash that is getting trapped on traps and SIMS prior to, specifically traps, prior to a WFGD measurement. In other words, the inlet side of your measurements. A lot of those things are now known. There are some very good companies out there that can do a 30B very reliably with speciation very reliably. So the question becomes, finished answering your kind of third question, which do we rely on? Quite frankly, we like to have both, because without those two, you're still kind of assuming that one of those is right. But I'll tell you what, if I have the one or two that I know are very good at making these measurements, I'll rely on them every time, because we'll get the correlations that we're getting. That'll be spot on.
Any further questions?
Keep in mind that mercury measurement is what you're driving everything by. So, you know, think about throwing up a blinder across your windshield and not knowing where you're going, knowing where you're going but not the direction you're going. Anyway, I'm sorry, go ahead.
David Heath with Dynegy. A question: you showed a solubility of mercury in your scrubber liquor. Did you measure the soluble mercury in your return from your filter, where you took your solids out, removed the solids, and then had your filtrate returned to your scrubber? Did you measure soluble mercury in that stream coming into your scrubber?
That's a great question. Again, the question is, do we measure the return water, the soluble mercury in the return water? Absolutely. That is absolutely key. And typically what you'll see, depending on where you make those measurements, you'll see changes in that mercury, soluble mercury. For example, if you take it from the blowdown at a hydroclone before you do the filtration, the soluble mercury in the liquid phase, which is, again, filtered through a 0.45, that's the definition of soluble mercury, will match fairly closely what is in the scrubber. As you go through, for example, the filtrate from the gypsum filtration, you'll get some dilution depending on how that water is dealt with and how much washing you do. You'll get some dilution, but there will continue to be a high level of mercury in that filtrate if it goes back to your scrubber. Absolutely. Again, another part of this is people have looked at this, fines that are separated from your gypsum byproduct are typically or could be returned back to your scrubber. Those contain high levels of mercury, and those will, although we think that those are solids as shown in this presentation, that solid mercury will in fact re-equilibrate within your scrubber and turn into high levels of soluble mercury. Could. I'm not saying that they will. They could. And so it is very important to do a total map Okay? Draw your box around your scrubber, but characterize everything that's coming in and going out. Absolutely. I'm sorry, a long-winded answer.
Any other questions?
Thank you.
Thank you, Bruce. You did a couple of things.